So let's move on to heat flow. So we've been talking about airflow. Mm-hmm. We've been talking about air moving inside and outside our thermal envelope. Let's talk a little bit about the heat flow. And this one isn't as long as the first one. The first one was the longest. But we have heat flow through three principles. Heat flows through conduction. And what I mean by conduction is heat flows from a warmer to a cooler spot. It's dependent on the R value that we've talked about a little bit and the temperature difference. Then we have convection, and that's heat that flows in air that's moving. Warm air rises, cold air falls. But also a forced air heating system is a convection system. We're moving heat through a moving airflow. So that's the second way we can move heat. And the third one is radiation, and that's infrared rays. And the good thing to get our head wrapped around that is the sun, a fire, or even a warm wall. If you get in the summertime, if the sun's striking a brick building all day long, and then the sun goes down, you walk past the wall, what do you feel? You feel the heat
coming right up off
it's
of it.
Radiating off that wall, and that's radiant heat. But I remember taking the boys to scout camp, and it could be nice and cold, and you stand around the fire, and what do you feel warm? It's not because the air is warm, it's because you got radiant heat.
Right.
The sun, even in the wintertime, if the sun's out, it feels warm, even though it's 10 degrees outside. That's radiant heat. So radiant heat warms the bodies that it strikes, or the objects that it strikes.
I have an apartment with self-facing windows, and I don't really need to heat my apartment a ton in the winter.
Because exactly.
Yeah, the sun just warms the space.
What happens is the sun in the wintertime moves to the south horizon. The sun goes basically straight over in the summertime, and then as we get towards winter, it moves to the south. And so it strikes our south windows, and you really don't get direct sun through the windows in the summertime.
Right.
But if you had east and west, you would get a ton of sun.
Yeah.
And so, the radiant heat in the wintertime on south glass is great.
Yeah. Saves me a lot of money.
Yeah, exactly. Because it warms up the space real nicely. And if it's shining on the furniture, whatever, isn't it warm?
Yeah.
It's warm. So, we want that, we call it passive heat. That's a bonus. And it happens even if it's 10 degrees outside.
Yeah.
Because it is not dependent on the temperature of the air. It is in a wave that's moving from the sun way out in space.
Yeah,
and
exactly.
if you're in space with no atmosphere, it's cold, cold, cold.
Yeah.
But that radiant heat is still moving through it in the infrared rays. So, those are the three ways that we have heat flow. And we'll talk a little bit about each one of those. And we talk in buildings and in load calculations, we talk about winter heat loss and summer heat gain. And let me just describe that so everybody understands. In the wintertime, we have a house, and it's cold outside and it's warm inside. Heat flows from warmer to colder, and so we lose heat, right? Mm-hmm. So we lose heat. In the summertime, what happens? We're trying to maintain 75 degrees or whatever inside. And what is it outside? It's 95 or 100. Mm-hmm. And so what do we have? We have gain. We are gaining heat inside. And so through this thermal envelope, we're getting heat coming into it, or we're losing heat. Mm-hmm. In either case, we're having to do something that requires energy. In this case, we add energy to make heat. In this case, in the summertime, we use energy to remove heat through the refrigeration process. Mm-hmm. And so in either case, it takes energy to remove the excess heat or to add heat back to our home. So it's a loss that we have to make up in the wintertime, and it's a gain we have to get rid of in the summertime. But both cost energy.
Yeah.
So Let's talk about conduction, the first one. And I don't know if you've ever gone out with friends and you go to the mountains and you're going to roast hot dogs and you don't have any sticks, and so someone gets a coat hanger out. And I don't know, have you ever cooked a hot dog on a coat hanger?
I have not.
Well, I've tried it. Or a piece of, if you use a piece of metal, you straighten out the hanger, you put the hot dog on it, and you stick it in the fire. And within 30 seconds or so, what's going to happen?
You're going to burn your hand.
You're going to burn your hand. Why? Because the wire coat hanger is a great conductor, has no R value. And so the heat comes right up it, and it's conducted up that wire, and the heat goes from hotter to cooler. Well, my hand's a whole lot cooler than the fire.
Right.
And so that happens. So if you go and buy hot dog sticks, they're going to have a wood handle and then the metal, because the wood handle's insulated and you won't get the conduction through the wood handle. And so conduction is simply you heat one end, and if it's a poor insulator, if it's not insulated, if it's metal or aluminum frame on a window or whatever, you're going to have heat conduction. And so with conduction in our buildings, we try to figure out ways to stop the conduction of heat through our building envelope. And we'll talk about that. We've already talked a little bit about insulation, right? Because insulation blocks that conduction. The next one is convection. Remember, we talked about that one? And that is air movement. And it's heat transmission by circulation of a liquid or a gas being the air. And it's like opening a window. Remember all the holes in the building? That's convection. We have heat transfer, whether we're leaking heated air out of our building or we're leaking cold air into our building, we end up with a heat transfer. And then our last one is our radiant heat. And that one's, that one's kind of cool because, it radiates off and it warms objects. I used to have a radiant heater in my garage because I could go out, my garage could be cold, I could turn it on.
And it's great in the winter.
And if I was underneath it, I was warm. Didn't warm my feet because the concrete was so cold. But it radiates just like your south-facing window. So if we can't talk about heat without talking about BTUs. Now, BTUs are just one of the units of measure for heat. And one BTU is the amount of heat required to raise 1 pound of water 1 degree Fahrenheit. Or it's about the same amount of heat that's produced by a match head. But we use BTUs to talk about how much heat we lose out of our house or how much heat we gain into our house. And so it's just a unit of measure. It's like gallons or whatever, it's just a unit of measure of heat. And I mean, that actually means nothing other than, it's a small amount of heat. So this is a thermal image taken with a FLIR camera, and this camera sees heat. I know you might be familiar with these.
Like infrared?
Yeah.
Yeah, okay.
Yeah, infrared camera.
Yeah.
They just see heat. So this is a picture inside, actually it's taken inside my living room at my house.
How did you get this in your house? Huh? Do you have a camera? Like, what
I
are
do.
These? Okay.
I have one. I have a infrared camera. And so let's just think for a minute about what this picture is telling us. I'm going to open this.
So we're the warmer toned.
Well, there's a little guide here.
Okay.
So the warmest, and depending on what you look at, the camera automatically adjusts.
Right.
And so it has a scale here. And what this is telling me is we see anywhere from 58 to 68 degrees.
Okay.
And 58 is, of course, the darkest, and the brightest is the warmest.
Okay.
So now there's a window over here, and so the reflection and stuff through the window I'd have to change settings on the camera to get an accurate reading here. So we'll ignore this part.
Okay.
But from here over, we can see So what do we see that's 68 degrees over here?
Whatever this is in the corner.
Yeah, it's one of those old antique pump organs. So that's the little, and why is it the warmest? Because it has no contact with outside.
Okay.
It's sitting away from the house, from the wall, right?
Uh-huh.
So it's going to be the very warmest because it's sitting at room temperature.
Okay.
Now, in between here, and in fact, right there at that spot, it's 64.2 degrees.
Mm-hmm.
If that was moved over to here, it would probably be like 66 degrees.
Mm-hmm.
Why is it warmer here, and why does it get colder as we move this way, and even colder when we get over there?
There's got to be some heat loss or heat transfer.
There's more heat loss. So let's think about this. So it's winter time, and cold doesn't come in, but heat leaves.
Mm-hmm.
Well, this thing is sitting in the air, and it doesn't have anything taking heat away from it because it's surrounded by 68 degree air. The drywall right here, that's somewhere around 66 degrees, it has insulation on the other side of it. So some heat is being pulled away, but the insulation is stopping most of it.
Right.
And so some heat is leaving and going to outside. And so it's cooled this down just a little bit. But when we get over here, this is a stud.
Mm-hmm.
This is a wall stud. Now the R value of wood is less than the R value of insulation, but it's still better than nothing.
Right.
So it's about R1 per inch. So that's a 3.5 inch stud with 1/2 inch OSB on the outside. So it's about R4 here, and it's like R11 or R12 here.
Mm-hmm.
And so that tells us, that we have more heat being lost to outside through the stud. So what are these little spots? Why do we have more heat loss there? Because those are the screws that hold the drywall on the stud.
Okay.
And because they go into the wood a little ways, we're losing some of the insulation effect because they go deeper into the stud, and so those are going to be colder.
It's crazy that it picks that up, but it's so detailed.
It picks that up.
Yeah.
So why is the corner so bad?
Because it's an intersection from
It's an intersection, and the way they framed it incorrectly. They didn't use advanced framing principles, and there is no insulation in the corner because they put a couple of studs, and there's a little cavity with no insulation.
Okay.
And you take it a step further, it's a corner of the plywood, the OSB, and I'm sure it's not sealed very well. It's probably a loose fit. So what do we have? We have air movement in and out of that corner. And so it's 10 degrees colder because we're losing heat at a greater rate, or we have a heat flow because we don't have what? We don't have any R value to resist the flow of heat.
Right.
So if we can do something to minimize the heat flow, what do? We reduce our energy consumption.
Mm-hmm.
So R value is whatever resists the flow. We have good R value here, so it resists the flow. We have less R value here, so less resistance. Where the metal screws are that go part way in the stud, even less. And where we have no insulation, we have even less. And R is resistance equals 1 over U, and we'll talk what U is in just a second here. So the formal definition is the inverse of the time rate of heat flow through a body from one of its bounding surfaces to the other side for a unit temperature difference between two surfaces under steady state conditions per units, blah, blah, blah. Basically what it's saying is R is the inverse of the rate of flow. So we have a certain rate of flow through that wall. Where it's insulated, we have a certain rate of flow through the stud. The higher the R, the less flow.
Mm-hmm.
When we get to U, I think it will come together a little bit better. So R just resists the flow.
Okay.
And that definition, unless you read it 50 times, it doesn't make a lot of sense. So let's talk about U factor. And it's interesting. Let me just make a point here. We typically rate insulation products in R because I don't know why but that's the way it's always been.
The standard.
It's the standard. But we rate windows or fenestration in U. And if you look at this, R equals 1 over U. And if you remember your math, if R equals 1 over U, then U is going to equal 1 over R. They're just reciprocals or the inverses.
Right.
Right? So U factor, or thermal transmittance. So the first one was thermal resistance. This one's transmittance. So a high U means that the heat flows real good. So it's the opposite. We want a low U or a high R.
Okay.
That makes sense, doesn't it? Or
Yeah.
how quickly or easily heat flows through a material. So it's the inverse of R. So U equals 1 over R. And this one's a little bit easier, I think, to get your head wrapped around. If I just read the blue text, time rate of heat flow per unit area and unit temperature difference. So really what's that saying is the U equals what I've put in below, the heat flow through 1 square foot per degree temperature difference. So if I have 1 square foot of this window that has a U factor of 0.35, if I have 1 square foot of window and it's 1 degree difference in temperature between inside and outside, I'll have 0.35 BTUs flow through it.
Okay.
If it's 10 degrees different between inside and outside, then I'll have 3.5 BTUs flow through that 1 square foot. And if it's 100 degrees difference in temperature, then I'd have 35 BTUs flow through that 1 square foot. So where U is really, really valuable is if we know the U of a wall or a window or anything, and we know the temperature between inside and outside, we know exactly how much heat is going to go through every square foot of that wall or window or whatever. And so for our load calculation, all we do is say, I have 300 square foot of window, here's my U factor, here is my temperature difference, and I can tell you exactly how many BTUs will go through there at that temperature difference.
Is that a good rated window?
That's a good window.
Okay.
But let's think about it. Now, we've been talking about R values, and a good insulation in a wall is R19 or 20 or 21. We talked about R8 on ductwork, which I think is too low. We put R38, R49 in attics. And I don't want to put you on the spot, but maybe we will.
Oh, no, don't make me do math.
If that is our U, a 0.35, and we know that R equals 1 over U, right?
Yeah.
The inverse, the opposite of that one. R equals 1 over U, so 1 divided by that is going to be roughly 3. 1 divided by 0.3333 would be 3.
Yes.
Right?
Yes.
So that's not a bad window, but it's only R3.
Okay.
So what does that tell us? That our windows are a weak component.
And they'll always be one of the weakest parts of the house.
They always will be. In fact, a really good triple glazed window that has 3 panes of glass instead of 2 has a U factor around 0.2, which means 1 divided by 0.2 is 5.
Yeah.
So a really expensive good window still is only an R5.
And in price difference, is it even worth it at that point?
No, they're not at this point.
Yeah.
Maybe in the future they will be, but not at this point. Okay, we just talked about windows and calculating the heat loss through some windows. Now let's move to the next step, our total heat loss calculation. Let's talk a little bit more about the same thing. Manual J, I have a picture of it here, is required by code to do for residential homes. We need to do a load calculation, and that's to size the furnace of air conditioners and furnaces. Remember we talked at first why don't we just pick whatever furnace, whatever air conditioner, and just throw it in? Well, as we've studied and talked about building a good thermal envelope and reducing air leakage and all those things, we also talked about we can have a smaller furnace and a smaller air conditioner when we do these things right. So when we do these things, we need to know how to calculate the furnace size, the air conditioner size. And so we use Manual J, which is the industry standard for residential load calculations. And knowing the R value, which we just talked about, and the temperature difference, the heat transfer through a specific component may be calculated. Just as we calculated for a window, we can calculate it for any other product. Now, we talked about the window. In fact, if I back up a slide, I'm going to do that just for kind of a refresher. Remember, we decided this 0.35 window is about an R3 window. And we decided that with 1 square foot of glass and 1 degree Fahrenheit difference, we'd lose that many or flow that many BTUs through that window. Or 10 degrees temperature difference would be 10 times that much, and so on. And then as you do multiple square feet, then you just multiply by the areas. So jumping to the heat loss calculation, we know the R value, and by knowing the R value, we know the U, because all we have to do is the math. So we can calculate the U based on knowing the R, and we know the temperature difference, then we can calculate heat transfer through a specific component. So heat loss, and stop me if you want me to go over this, but I think it's pretty straightforward. Heat loss equals the area times the delta T, now that's the temperature difference, divided by the R. But if we have windows, we know that 1 over R equals U, so we can do area times the delta T times the U. And it's the same thing. Instead of dividing by R, we're multiplying by U, and we get the same result. So if we have an example, we have 300 square feet, and the previous one was a 0.35 window. We now have a 0.3 window, which is just a little bit better than R3. And I put in a 60-degree delta T. So let me explain what that delta T means. That means if it's 70 degrees inside and it's 10 degrees outside, we have a 60-degree delta T. It's the temperature difference between inside and outside. And if we remember the definition of the U factor, for every degree Fahrenheit, we will have 0.3 BTUs transferred through 1 square foot of window. Well, we have 60 degrees Fahrenheit, and we have 300 square foot of glass, and so we simply take the area from the formula above, which is 300, times 60, which is the delta T, times 0.3, which is the U factor, and we get 5,400 BTUs. That's how many BTUs of heat will be lost through 300 square foot of window. And that's about the average window that you'd see on a 15 to 2,000 square foot single story house.
That looks like a lot of heat loss. Is that a good or bad window?
Yeah, that's a good window.
Okay.
That's a pretty darn good window. 8 years ago, when we really started getting active on energy code, and 8 to 10 years ago when we really started pushing it, the code requirement was prescriptive table was 0.35. And some manufacturers struggled, 0.35, 3.4, 3.6, 3.7 was where a double pane vinyl window with low E coating on the glass ended up. Well, with improvements they've made over the last 8-10 years, it's real easy and real common to see 0.3, 0.32 on the windows. So they've dropped just little bits, just with the manufacturers improving their components. Still 2 panes of glass, still low E coatings. I'm not sure everything they've done to get there, but 0.3 is a good window. We are seeing AMSCO makes a double coat window, and so they have coatings on both the outer pane and the inner pane. And with that, we're seeing windows that are with just 2 panes of glass coming in at 0.28 and 0.27, which is really good for 2 panes of glass. If someone would have submitted that 7 years ago on a res check and said that I have 0.27 windows, I would have told them, no, you don't. Show me.
Yeah.
So no, that's really good, and doing it with just 2 panes of glass instead of the third, which gets really expensive. That's pretty good.
Yeah.
One of the things that this kind of points out, this is an R3, just a little bit better than R3, so it's like R3.2 or something like that was where it would calculate out. If you minimize the amount of window you have, so you don't have huge amounts of window, and then you make really good walls that are like R24 or something like that, you can see that you could end up with a pretty low, load calculation, because windows are going to be your biggest, and you can end up with your walls, or might be just 1,000 BTUs or 1,200 BTUs for all your walls. And it's not uncommon to see a 1,500 square foot house come up with a total heat loss of, under 20,000 BTUs, maybe in the 15 to 16,000 BTUs. And that actually creates problems because they don't make a lot of really small furnaces. And so the smallest furnace is bigger than you need.
Yeah.
In a lot of those cases. So there's one thing I just wanted to touch on real quick, and we talked a little bit about this earlier. We really aren't going to, it doesn't apply too much as far as heat flow by conduction, but it's heat flow by radiation. And this is the solar heat gain coefficient. Now this label, and I did not mention it before, this is the label that comes on a window. It's a standard label, it's an NFRC label, and it has a couple of things on it. U factor, which we already talked about, and we need to know that, and the code has a requirement there. And then we have the solar heat gain coefficient. And these are 2 numbers that are required by the code. When we get into visible transmittance, that is starting to apply to our commercial code, but not on our residential code. So we know what the U factor is. You mentioned south-facing windows. The solar heat gain coefficient, it's again a number that's less than 1, but this is a percentage is what it's giving us, and what it's telling us is 32% of the infrared heat in the sun's rays are going to make it through the window, which means 68% is reflected away.
Okay.
So if you had a solar heat gain coefficient of 0.2, then only 20% of the heat makes it in, and 80% is reflected back out. So a low solar heat gain coefficient, or SHGC, is wonderful on your east-west glass summertime. Now on your south-facing glass that you mentioned, south-facing glass, if we have a low solar heat gain coefficient, we block some of that heat that's available. Now that might cause a challenge though. My previous home had my office, my study, faced south, and it had big tall windows.
Oh no.
And so in the wintertime, what would happen is just that room and the living room had south glass. And so
They'd heat up.
they would heat up. And then the rest of the house, and the thermostat was back.
So you were sweating.
There's one in the master bedroom, and then there was one over in the hall by the kids' bedrooms. And so those thermostats didn't see the heat, which is good because the majority of the house did not see that.
Yeah.
Not see that heat. So we needed the furnace to run so those would stay comfortable.
Yeah.
And my office would get so warm sometimes that I'd actually crack a window because it was too hot.
Yeah.
Now they do have passive designs in homes that you heat up a masonry wall or something and the heat radiates through, but they're kind of impractical you can't do that with every style of home.
Right.
And so, with an apartment or something that's, open into most of your living space, so you have a bedroom and then you have a living area and they both face south. That's great. The only thing that maybe your kitchen and bathroom and stuff don't see that heat. But
yeah. I
but
think it's
everything
only
else
the
does.
bathroom. Everything else is heated up.
Yeah,
so.
everything else heats up.
Yeah.
So, yeah, there's absolutely nothing wrong with passive radiant heat. It's just sometimes you have some temperature differences and you struggle a little bit with that.
Yeah.
So we've talked about insulation a little bit, and we've talked about the R value, which which is assigned to the insulation. We really need to talk about poor installation practices, and in fact, I think we really need to do a podcast that's just focused on proper installation techniques, because I see so much that's installed incorrectly. And I took all these pictures. These aren't from someone else. These are pictures that I took. And we'll talk a little bit about it. Proper installation of insulation has no gaps or voids. It has insulation behind boxes, around pipes and wires. So if we look at this, and it doesn't have any compression. So this is a garage ceiling, and I don't know which way I should tilt this picture, but the garage door is down here,
Okay.
and I'm looking up, so this is the ceiling of the garage. And you can see these fiberglass bats, and you see how they've kind of folded them under,
Yeah.
so you can see the ends. You see how they've done that?
Yeah.
And what they've done there is they haven't cut them to fit. And so
Okay.
by compressing it, you're pushing that air that we want static or stagnant within the insulation. You're pushing the air out, and you're reducing the R value of the insulation. So compressing the insulation reduces R value.
Okay.
These wires.
Is that
they're-
just laziness? They didn't want to
it's-
cut
yeah,
it?
That's exactly
Okay.
what it is.
Okay.
They didn't want to cut it to fit it. Here's some wires running across. This is a wall, and you can see them, and they've just kind of tucked up against one side, so it's going to be bowed out there, and we have all these air spaces.
Pockets, yeah.
And when you have air pockets, what do? You have the ability for air to
Get in there
start
and
doing this
circulate.
convecting
Yeah.
and circulating in there. So again, we've compressed the insulation, and we've created an air space which promotes convective flows within the insulation, where if we had it fitting tight and snug and in full contact with the drywall on this side and the drywall on the other side in the garage, then everything would be good. So this should have been cut at the wires, and so it fits around the wires.
Right.
You cut it and pull half of it back, and the wires are all hidden inside the insulation. So there's no compression, and you have continuous insulation. And then here is one that is just 100% laziness. When they insulated this one, and this is on a remodel, pull the drywall off, and you can see they just tucked it behind the box.
Ugh.
And so you have a space about this big behind the box. And proper installation on that would be you cut the insulation to fit the box, and then you have a little piece that fits behind. Mm-hmm. You're not going to get full depth because of the box, but if you just cut it and bring it all out front, and you don't put something behind, then you have that little airspace behind it, and it's not fully insulated.
Yeah.
Which kind of, when we think back about the wall insulation where they blew the insulation in it with a net and blow, that's perfect for every one of these. Because why? Because it's full. It automatically conforms to the boxes, to the wires, to everything.
Gets all the gaps.
Gets all the gaps. We don't have any compression. We don't have any reduced R value. We don't have any air pockets. And we have a quality installation. And it's an effective insulation. Where someone is living in that house, and they're never going to know that they could save if their house had been insulated to a higher level. And maybe it's only 2 or 3%. But if it's 2 or 3% on this, and then 2 or 3 or 4% on better air sealing and on a better duct system and sealing your ductwork, every one of these little pieces adds up. And by doing everything right, you can have a substantial savings on your energy.
So it sounds like you don't regularly see bat insulation installed correctly.
I almost never see bat insulation installed correctly. In fact, I have some pictures of properly installed bat insulation that I probably ought to put in one of my presentations.
So we know it exists.
Yeah, because I bash poor installation all the time, and on our friends that are HERS raters and everything, you've probably heard some of them. They just go off on how horrible installation is installed. And it's a crappy job. It itches, and it's not the funnest job in the world. But to do it right, just takes a little more effort. They're getting paid by the square foot, and they just want to get it in there.
And they do not want to cut anything, it looks
Yeah.
like.
Now this one, the insulation had been pulled out, but there was a little piece that was fitted in there. You see how we have these little spaces? Those are often not cut right, and then they're just kind of jammed and packed in there.
I can see that. Especially by the way these ones look
Yeah.
over here.
Yeah, exactly. The same
It
type
almost
of
looks
thing.
like trash was just shoved in the wall.
And so if we don't have insulation and air barriers aligned, we have those air spaces, and we have those convective flows again with air that can move around in there. Because what's the air going to do? It's either going to see a warm surface or a cold surface, and then it's going to start moving. Why? Because of convection, it rises. And then we just get this circulating air in that cavity, and less R value. And it's simply because they failed to cut and fit it. And you know what? And I'm not going to blame it all on the installation people. I remember it's probably my first year I was doing inspections. I went on an inspection, and it was really bad, the insulation, and I failed the insulation. And the builder called me just freaked out. No one fails insulation inspections. And I says, well, that's because no one's requiring you to do it right, because none of the boxes were done correctly. Instead of doing this, it just came out and wrapped around, and so you had a gap here and a gap here, and it was just really poorly insulated. If we understand the building science, we know that we need to do better.
Right.
And so our net and blow insulation, we saw it on a ceiling. Here we see it on a wall. And they've done a nice job. Here we have an intersecting wall, and they've put blocks across for backing on the drywall, and that allows insulation to go behind it. Now, if you were putting batt insulation in there, no one would cut that batt insulation to fit around those little 2x6 blocks. They would just tuck it underneath, and it would never be done correctly.
Right.
So the blown insulation gets behind that intersecting wall. Notice this electrical box.
Yeah.
It's fit
Yeah.
just automatically because of the way they blow it in there, it fits right around it.
It's more tailored.
It does.
Like a tailored look. Clean.
It looks
yeah.
clean. Everything fits. It's it has a finished look to it, doesn't it?
Yes.
No voids. It fits around everything that's in the wall cavity. See, I'm guessing this is a pipe to a hose bib going, out through the wall. And so where it goes through the wall, it's going to fit right around it. There's no trying to cut and fit around it. There's no air spaces for that convective airflow. Yeah, I love this. And for building inspectors that might see this, if you required them to do the batt insulation correctly, they would automatically say, you know what, it's not worth it. We'll pay the extra money for the bib, for the net and blow.
So it is more expensive than...
It's a little bit more.
Yeah.
It's a little bit more.
And is it easier installation process, or is it harder?
Well, I've never done net and blow. I've seen it
Okay.
done. I've seen it done a bunch of times.
Yeah.
I've done batt insulation on my own stuff.
Yeah.
And it's a pain to do it right.
Yeah.
And of course, as I've gotten older and more educated on this, the last batt stuff I did as I was remodeling, I did a really good job. You know what I mean? I took the time. To do batt on this would just be brutal. To try to fit it into this area,
Yeah.
it would be really tough. And I would much rather staple netting up and blow, or have someone do that, than have someone do batt for me, just because it's so obvious that it's going to do a better job. And the R value, the very best you can get in a batt in a 2x6 wall, and this I believe was a 2x6 wall, the very best that you can get is about R21. With some of these blow materials, you can get R24.
Oh, wow.
So you get more R value, across the board when you use net and blow over bat. You can buy bats for 2-6 walls that are R19, so you can get 19 and 21, but then you can get between 21 and 24 with the blown insulation.
So would you see a house with a mix of both ever? Like both insulation batting and blown? Or
We do a little bit. In fact, the cantilevers we saw, those were on houses that had this in the walls.
Okay.
And so it kind of baffles me that they maybe the cantilevers are a little tougher to net.
Yeah. That makes sense.
To get under there, they're going to be a little tougher. But yeah, it's. I'm not a huge fan of bat insulation anymore. Obviously, I think it's pretty obvious, isn't it? Yeah. So, no, this is great, and I really do believe that if we required bats to be done properly, they'd probably charge you more, and so it'd be just as cost effective to do this. So this is a great package. Now I know some houses you just, they're on a pretty tight budget, but have a challenge with, we can't afford to do it quite as good and save a little bit of energy, and so we do it a little bit, so we use a little bit more energy, How does that really work out?
Right.
Aren't we better off spending a little bit more right now and then save energy for the whole life of the building?
Yeah.
Because once you build the wall and you insulate it and you cover it, no one's going to come back and say, well, they didn't cut around my boxes. Let's fix that.
Yeah.
Unless you do a remodel and tear it off. So we typically do get a higher R value. So we're talking about heat flow through the buildings. What are the effects of heat flow on our buildings? These are similar to airflow, health and safety. Mold and mildew, where moisture carried in heat flow contacts cold surfaces. So let me explain that a little bit. We talked earlier about if we have air leakage, if we have moist air and through positive pressure we push it into our wall cavities and it gets to the sheathing, it will condense inside the wall.
Right. Or
the rim joist, and we get mold growth. Well, heat also transports moisture. So warm moist air moving to outside will also transmit or transport moisture in through the insulation and against the cold surfaces. So whether it's air or heated air, we're still going to move moisture, and we're going to have the same problems, and we still will have mold and mildew where moisture is carried in a heat flow. And where we really notice this is going up through roofs.
Okay.
And we have a lot of buildings that are built without trusses and attics, and so they just have a big rafter that will rise with that heated air through the insulation, and we have a mold issue on the underside of the roof deck. Heat flow, we can have some comfort issues, as we mentioned a little bit earlier, I think. If you have that single pane window or a pour window, even if it's air sealed, if it's cold, we're going to get the cold air dropping off it, and it's going to create a draft, a circulating draft. Building durability, this is the big one. Those pictures of mold, that building was 8 months old.
Wow.
It was brand new.
So just bad building science.
It was misapplication of building science. Yep, it was bad building science. They didn't recognize building science. They didn't build to code.
Yeah.
And, the builder missed it. The inspector missed it. It's in a crawl space. No one wants to spend a lot of time down there. And they had a big issue. And, it took some expense to fix that, quite a bit of expense to fix that. So moisture moves with heat flow, and the moist wood also, it rots. And there's so much civil litigation going on right now with moisture and what it does to building components. And then on top of that, we have the energy efficiency. If we have excess heat loss or gain, we have areas not insulated properly, so we're using more energy for heating and cooling to replace that heat that we're losing. So these pictures almost look the same. We lose heat through air leaking through it, and we lose heat through the conduction through the building components. So the convection, the air moving through it, the conduction, the heat moving through the products.